Did you know that life on Earth may not truly belong to Earth at all? That the universe itself, its silent architect? Every breath, every cell, every heartbeat still carries the imprint of the cosmos that made it. When the summer sun rises over the Alps, every blade of grass and fluttering insect seems perfectly tuned to its world, yet their harmony began far beyond it. The warmth that wakes the flowers comes from a star sculpted by gravity. The air that fills your lungs was forged from the ashes of ancient suns. Even the water beneath your feet arrived from frozen worlds that once circled elsewhere. The story of life is not just a tale of biology, but of astronomy, a history written in starlight. To understand who we are, we must first look outward to the universe that shaped us. Picture the Earth 66 million years ago, quiet and unbroken. No flash in the sky, no mountain of fire falling from space. The Yucatan Peninsula is just another coastline washed by calm waves, its jungles alive with the calls of creatures that would have ruled forever. The air hums with the deep-throated cries of tyrannosaurs. Titanosaurs move like islands of muscle through forests of fern and magnolia. We are standing on that world warm, heavy, endless. The continents drift slowly beneath a sun slightly dimmer than ours. Clouds coil in slow motion over oceans where ammonites spiral near coral shelves. Everything seems eternal. But eternity is stillness. Without catastrophe, evolution sleeps. Mammals remain small nocturnal eyes reflecting moonlight. Intelligence, if it sparks at all, hides in the dark under roots and stones. Scientists recreate this timeline with simulations. In their models, there is no human future, no language, no metal carved into telescopes. The Earth becomes a grand cathedral of reptilian power, stable and unchallenged. Even the stars above would rise over a planet that never questions them. Now, close your eyes. Feel the soil beneath your feet untouched by the crater that never formed no 180-kilometer scar, no rain of molten glass, no layer of iridium dust. The air remains rich with carbon, the oceans warm and glittering. It is a breathtaking, motionless Eden, beautiful, unchanging, and doomed to never dream. Walk with us along the quiet hills of Gubbio, Italy. The air smells of stone and moss. Before you rises a grey cliff of limestone layered like pages of a cosmic diary. In the middle of those layers lies a thin line of clay only a few centimetres thick, yet it divides the history of life in two. Beneath it lie the bones of the Cretaceous world, above it begins the age of mammals. That fragile stripe is known as the KPE boundary, and inside it scientists found a mystery made of metal. In 1980, Luis and Walter Alvarez analysed this clay and discovered it contained unusually high levels of iridium, about 100 times the amount normally found in Earth's crust. Iridium element number 77 is a heavy silvery metal born in the hearts of dying stars. It is rare on our planet's surface but abundant in meteorites. The same iridium-rich layer appeared in Denmark, Tunisia, and across the Pacific seabed. Everywhere the signature was identical, as if the whole Earth had been dusted by a single planetary breath of metal. Now close your eyes and step back in time. A celestial rock roughly 10 kilometers across plunges through the atmosphere at 70,000 kilometers per hour. Air itself ignites. The object strikes the Gulf of Mexico, carving a crater 180 kilometers wide and 20 kilometers deep, larger than the distance between Brussels and Paris, deep enough to drown the Himalayas. The impact unleashes energy greater than 1 billion nuclear bombs. Firestorms sweep the continents. Oceans rise and boil. The planet turns briefly into a furnace of glass and wind. Today, that ancient scar still whispers beneath our feet. The iridium in the rocks of Gubbio and in countless other places remains a metallic memory of that day when the sky fell. Each atom is a relic from a dead star, a particle of a larger story, the story of how catastrophe sculpted creation. Hold that image in your mind, a single line of clay, no thicker than a hand, carrying the weight of an entire world's extinction, and the quiet promise of what would rise after. Now, take a slow breath. The world is calm for its final heartbeat. Then the sky splits open. A light brighter than 1,000 suns ignites above the Gulf of Mexico. In a single moment, night and day lose meaning. The asteroid 10 kilometers wide, heavier than all the cities of humankind, combined strikes the Earth at 70,000 kilometers per hour. The ocean lifts like a curtain of glass. The crust ripples outward, liquefying under pressure greater than any weapon could ever deliver. For one instant, Earth itself sings a low metallic note that would echo through the mantle for centuries. The crater that forms stretches 180 kilometers across 20 kilometers deep enough to swallow entire mountain ranges. Energy released roughly 10 to the 24 joules over a billion nuclear detonations unleashed at once. We can almost feel it. The wind transforms into a wall, scouring the surface clean. Shock waves move faster than sound, flattening forests on continents thousands of kilometers away. Every tree bends in the same direction. Every living thing that breathes is thrown to the ground. From the sky, fragments of molten rock rain down tiny beads of glass called tektites, glowing red as they fall through the darkness. Within minutes, fire consumes the planet. Flames race across continents. Oxygen itself becomes fuel. Rivers boil. Asphalt seas spread across plains of fern and magnolia. The light of the sun is replaced by the orange of global firestorms. You can almost smell the air, dense, metallic, bitter with smoke. Then, as quickly as it came, the world dims. The impact has thrown billions of tons of dust and sulfur into the stratosphere. Sulfate aerosols spread, forming a pale mirror that reflects the sunlight back into space. The temperature drops by tens of degrees. Photosynthesis halts. The ocean surface chills, turning dark green and silent. Plankton die first, then fish, then the reptiles that hunted them. For months, maybe years, the Earth remains wrapped in shadow. Acid rain hisses across continents, etching the bones of forests. Rivers run black. Even the sky itself glows with a dull red twilight, as if the planet mourns. Scientists today still find its signature shocked quartz soot, iridium microscopic glass beads, spread evenly across every ocean and continent. One layer of clay just a few centimeters thick holds the memory of this instant, the day everything ended and something new began. Because from this ruin life will claw its way back. In the quiet ash, tiny mammals rise scavenging under ferns that return first to the wasteland. Evolution restarts, guided by the same invisible hand that once delivered destruction. The world is no longer the same. The dinosaurs have fallen silent. The stage is cleared for a new voice to emerge, the voice of curiosity, of memory of us. The world never truly recovers from impact. Yet even after the fires fade, the planet remembers the rhythm of catastrophe. Extinction, it seems, is not a single event, it is a heartbeat of the cosmos. From the silence left by the dinosaurs, let us drift further back in time, long before reptiles or forests, long before the continents took their present form. Travel with me to an ocean planet 445 million years ago, when almost everything alive existed beneath the waves. You are standing on the shoreline of ancient Gondwana. The air is thin and raw. There are no trees, no birds, only mosses clinging to stone, and endless water stretching into a grey horizon. Beneath those waves life thrives. Trilobites with crystal eyes, coral gardens glowing with colour, cephalopods as long as buses gliding through the shallows. The sea is a cathedral of motion, every current alive with plankton and light. Then suddenly something shifts. Temperatures fall. Ice begins to spread from the poles, locking away the oceans in white. The water level drops, swallowing coastlines. Oxygen levels fall. Entire reefs vanish. Scientists call it the late Ordovician extinction, the second most severe in Earth's history. In just a few million years, barely a blink in cosmic time, about 85% of marine species disappear. Why did the planet turn against its own abundance? Some geologists point to volcanic activity and the pull of shifting continents. Others, more daring, suspect something else, an influence not born of this world. Perhaps they argue a cosmic event touched Earth once more, a sudden storm of radiation, an invisible fire that burned through the sky. You can almost feel the weight of that question. Standing at the edge of the Ordovician Sea, watching the tide retreat, you sense that the universe itself is not a passive backdrop, but an active sculptor. It builds it, destroys, and it begins again. The evidence we hold is fragmented, a puzzle made of fossils and isotopes, but the mystery remains. If the heavens could erase life once with a rock, perhaps they could do it again with light. And that is where our journey continues toward the possibility of a cosmic weapon, unlike any other one, made not of matter, but of pure energy. Let's move beyond Earth's quiet oceans and step into the vast black, the true forge of extinction. Far across the galaxy, in regions where stars are born and die in violent cycles, titanic explosions ripple through the dark. These are gamma-ray bursts, the brightest and most powerful flashes the universe can create. For a few seconds, they release more energy than our sun will produce in its entire lifetime. You can imagine one now a massive star, perhaps 30 times heavier than the sun, burning its last reserves of hydrogen and helium. Its core collapses inward faster than thought itself. Gravity crushes the atoms into pure neutrons, forming a tiny sphere barely 20 kilometers across. From its poles, 2 jets of energy erupt, each a beam of radiation so intense it could sterilize a planet halfway across the galaxy. The light is invisible, but its power is unimaginable. Scientists classify them as GRBs, gamma-ray bursts, some lasting only milliseconds, others for minutes. Most occur billions of light-years away, far beyond our danger. But the mathematics offers a haunting possibility. If one such beam were to aim directly at Earth from within 6,000 light-years, the upper atmosphere would be stripped bare. The ozone shield, our planet's ultraviolet armor, would vanish within seconds. Imagine looking up and seeing no sky at all, only a harsh ultraviolet glare burning through clouds. Every ocean's surface would shimmer with death. DNA would unravel under radiation, plankton would perish first, and the food chain would collapse like falling glass. The world would dim, not from darkness, but from too much light. Astronomers trace these bursts to the deaths of massive stars, to hypernovas and the merging of neutron stars. The same process that forges gold and platinum in the universe also forges destruction. Even beauty can be lethal. Today our satellites, Swift, Fermi and Integral, watch the heavens, counting flashes that last less than a heartbeat. Each one is a message written in photons, a reminder that the cosmos is neither kind nor cruel. It simply acts. And perhaps somewhere in the Ordovician sky, one of those silent lances of light found its target. One invisible breath from across the galaxy, and an entire ocean world began to die. If the impact that ended the dinosaurs was a wound carved by stone, then the Ordovician extinction may have been a wound burned by light. No crater, no ash, no sound, only radiation moving faster than thought. Invisible, silent absolute. Picture Earth 445 million years ago. The oceans gleam under a pale sun. Trilobites crawl across the seabed like armoured leaves, and coral towers shimmer in shallow water. Then, without warning, the sky changes. For a few seconds, perhaps less, a distant star dies collapsing in upon itself. From its poles burst twin beams of gamma radiation, narrow as needles, crossing the galaxy like invisible swords. One of them points at us. When that light reaches Earth, it carries the energy of 100,000 supernovae. The upper atmosphere, once calm and blue, is ripped apart. Molecules of oxygen and nitrogen split. Ozone, the fragile shield that filters ultraviolet light, is annihilated. For days the planet glows with electric storms as ionized air recombines. To the creatures below there is no visible sign of attack. The sunlight seems the same, yet something essential is gone. Without ozone, the full fury of ultraviolet radiation strikes the surface. Imagine standing on a beach where every ray of sunlight burns through skin, through cells, through the delicate architecture of DNA. Plankton die first, bleaching the oceans into silence. Coral reefs crumble into bone-white ruins. Even deep sea life begins to fade as the food web collapses from the surface downward. The climate turns colder. Nitrogen oxides form a shroud of dark aerosols that block the sun, triggering an age of ice. It is as if the planet flinches, curling under a cosmic blow. The seas recede, glaciers expand. Continents groan under new weight. Scientists studying Ordovician rocks find chemical scars, sulfur isotopes, sudden drops in oxygen and patterns of extinction that begin in shallow seas before spreading to the depths. It fits too neatly to ignore. Perhaps not a meteor, but a beam of light itself erased the world. You can almost feel the paradox. The same light that nurtures life can also unmake it. In the vast laboratory of the cosmos, illumination and destruction are born from the same fire. The idea that a single burst of light could erase most of life on Earth remains one of the most haunting scientific proposals ever made. It feels both simple and terrifying. No asteroid, no volcano, just a silent wave of radiation sweeping through the atmosphere unseen and unstoppable. Among scientists, the hypothesis divides the room. Supporters argue that it explains what no other model can, the speed, selectivity and global symmetry of the late Ordovician extinction. A gamma-ray burst could destroy the ozone layer in seconds, allowing deadly ultraviolet radiation to pour in. It would strike the sunlit shallows first, exactly where the fossil record shows the earliest deaths. It fits, they say, almost too perfectly. Skeptics remain unconvinced. They prefer the comfort of visible forces, ice ages, volcanic eruptions, tectonic shifts. These leave traces, ash layers, carbon isotope changes, glacial marks on stone. Gamma rays leave none. They pass through the world without residue, destroying evidence as they go. To many geologists, that makes the theory poetic but unfalsifiable. Yet the probability is difficult to ignore. Astronomers calculate that once every few 100 million years, a burst powerful enough to sterilize half a planet could occur within 6,000 light-years. The galaxy, it seems, breathes danger. So the argument endures: was the Ordovician die-off sculpted by Earth's own rhythms or by a distant star's last breath until proof arrives? The question hovers like radiation itself, unseen, unresolved and waiting to strike again. The Earth healed, but the lesson of extinction remained. From the silence of the Ordovician seas, a question endures: are we shaped by chance or by the architecture of the cosmos itself? Each catastrophe leaves behind a blueprint, a kind of celestial design, etched into rock and bone, and perhaps if we look far enough, that same design can be found across other worlds. Let us move beyond our planet, beyond the thin blue veil of atmosphere, into a galaxy of worlds still forming. You can imagine drifting among them spheres of vapour and ice, molten planets glowing red beneath newborn suns. Every orbit, every tilt, every breath of radiation builds its own version of biology. The universe is an engineer of endless prototypes. On some worlds, gravity presses harder, sculpting life into dense, compact forms. On others, weak gravity allows creatures to rise tall and delicate as glass towers. Around red dwarf stars, daylight is crimson and long, and photosynthesis may unfold in darkness, drinking infrared light instead of gold. The architecture of each planet, the size, the distance, the parent star, becomes a silent law of evolution. Scientists call this the planetary architecture hypothesis, the idea that life's shape is written not only by chemistry, but by the geometry of the world it inhabits. Temperature, radiation, magnetic fields, even the neighbouring planets in a system all contribute to how a biosphere breathes. Imagine walking on a world where the sky never truly darkens, where sunrise freezes in mid-air, because the planet is tidally locked. On that horizon, day and night stare at each other forever, and between them lies a narrow twilight, a border where life might cling trembling but alive. We begin to see that life is not Earth's privilege but the cosmos's experiment. The same forces that ended the dinosaurs or froze the Ordovician seas are the ones still building new worlds. Destruction and creation share the same blueprint. Only the context changes. And so, as we peer into the void, we find not emptiness, but architecture, an unseen pattern guiding the rise and fall of everything that lives. From the idea of planetary architecture, let us travel 40 light-years away to a system that feels more like a clockwork dream than a set of worlds. The star is called TRAPPIST-1, a dim red ember smaller than Jupiter, yet surrounded by 7 rocky planets. Among them orbits TRAPPIST-1D, a world that lives forever on the border between day and night. Because it is tidally locked, one side of the planet always faces the star. There the sun never sets. The ground bakes beneath a crimson glare, mountains shimmer like coals. The other hemisphere is eternal darkness, glaciers 1,000 meters thick, temperatures far below the coldest Antarctic night. But between these two extremes lies a narrow corridor, a ribbon of dusk. It is called the Terminator Line, the zone of eternal twilight. Imagine standing there. Behind you burns a horizon of endless day, glowing red like molten iron. Ahead, the land fades into shadows where ice glows blue beneath a thin atmosphere. The air around you trembles with constant wind streams of heat rushing toward the cold, forming cyclones that never rest. You can feel the contrast on your skin, warmth on one side of your face, frost on the other. Scientists believe this belt could be the most stable region for life. Atmospheric models suggest that clouds might form a reflective dome over the bright side, cooling it, while winds distribute warmth toward the dark. In this balance, oceans could stay liquid mist drifting between light and shadow. Perhaps life could take root, organisms photosynthesizing with dim red photons, plants black or violet, to capture every ounce of heat. If intelligence arose here, it would learn equilibrium as survival. A civilization would watch 2 horizons forever, one glowing with fire, one whispering in ice. Night and day would not be opposites, but halves of a single breath. The TRAPPIST-1D twilight is more than a scientific curiosity. It is a parable written in orbit, Existence, it seems, endures not at the extremes but in the fragile gradient between them where contradiction becomes home. Between the eternal day and the endless night, the line of twilight becomes more than geography, it becomes a proving ground. Every gust of wind, every pulse of heat and cold is a trial. Here life would not simply exist, it would compete endlessly against the laws of physics themselves. Imagine standing on that frontier once again. Behind you the air burns, before you frost creeps across the sand. The sky's a split canvas, one half glowing crimson, the other a deep blue-black scattered with stars. Storms roar in the distance formed by the clash of extremes. Lightning flashes in the haze like a heartbeat. This is the arena of evolution, fierce, elegant, unrelenting. Scientists imagine that on planets heavier than Earth, gravity presses harder, sculpting every organism closer to the ground. Creatures there would be thick-bodied, their limbs short and powerful, their bones dense as iron. Even trees would hunch low bark smooth to resist the drag of dense air. Wings might never evolve at all, flight would be too costly. The landscape would feel compressed strength traded for motion. Now travel to a smaller world, one where gravity whispers instead of commands. Their air-thins mountains rise higher, and bodies stretch tall to capture what little warmth remains. You might see forests that sway like seaweed, plants shimmering like silk. In that lightness, evolution favours height and delicacy. Wings unfold. Life becomes buoyant. A single leap might carry you the length of a football field. Evolution is at its heart geometry in motion, a negotiation between physics and imagination. Each planet writes its own rules, but the strategy is always the same: adapt or vanish. Even on Earth we can feel this cosmic grammar in the shape of every living thing. The whale echoes the pressure of the sea, the eagle mirrors the thin air of the mountains. In every world, life and environment dance in conflict and harmony. The arena may change from oceans to deserts, from stars to shadows, but the principle endures. To evolve is to learn the language of gravity, light, and chance whispered by the universe itself. Every pattern we have seen so far, the balance of heat and cold, of gravity and air, leads us back home. The worlds of Trappist and their twilight belts show us how fragile equilibrium can be. But here on Earth that balance has held for billions of years. It makes you wonder, was our planet simply lucky or deliberately tuned by cosmic accident? Earth was born from chaos. 4.5 billion years ago, the young solar system was a storm of collisions, planets, forming, breaking apart, reforming. Among those fiery encounters came one that changed everything. A Mars-sized body, which scientists call Theia, struck the early Earth at a shallow angle. The impact nearly destroyed both worlds, vaporizing stone and metal, flinging molten debris into orbit. Out of that wreckage, gravity sculpted the moon. You can imagine it, the sky filled with rivers of glowing rock, the horizon smeared with light. The Earth turned molten, its day shortened to 5 hours, tides boiling across the surface. And yet out of that chaos came stability. The moon became our counterweight, our guardian, slowing Earth's rotation, calming its tilt and shaping the rhythm of oceans. Our world, it seems, was born from violence but gifted with balance. From collision came harmony, from destruction the pattern of life itself. And so the story continues from the accident that made the moon to the gentle pull that keeps our seas breathing in and out. The moon steadies our spin, but gravity itself shapes the essence of everything that breathes. It is the great sculptor, unseen, relentless, impartial. On our world it defines what can stand, what can soar, what must crawl. But imagine for a moment that Earth's pull was stronger not by much, perhaps twice its current force. The difference would be enough to remake the face of life. You would feel it instantly. Each heartbeat would work harder to lift blood to your brain. Your chest would ache beneath the weight of your own body. A single step might feel like wading through deep water. Buildings would sag. Bridges would need to be squat and wide. Mountains could no longer rise like spears. Gravity would sand them down into rounded domes subdued by their own mass. Even the air itself would grow denser, heavy with pressure, muffling sound, slowing wind. In this world, evolution would favour strength over grace. Plants would creep close to the soil trunks, thick as columns, leaves small to resist the drag of dense air. Animals would move low their muscles, dense bones reinforced like iron girders. Hearts would be enormous, pumping against the tyranny of weight. Wings would be useless. The dream of flight would never be born. You can imagine forests crouching under a dark, heavy sky, creatures breathing slowly, every motion deliberate. Yet a world of stronger gravity would not be lifeless. Its thick atmosphere would trap warmth, softening the seasons, calming the storms. Oceans would rise and fall sluggishly, their tides tamed even under the moon's command. It would be a world of endurance, not speed of patience, not motion. Civilizations there would grow inward rather than upward. Towers would crumble, but tunnels and domes would thrive. To its people, the sky might seem unreachable, a symbol of pressure rather than freedom. Gravity defines the scale of imagination. Hours at 9. 8 meters per second squared is perfect for movement, for flight, for thought. Change that number, and the story of life changes too. Perhaps in the quiet strength of gravity, the universe reminds us that every act of rising begins with learning how to bear the weight. Now imagine the opposite world, one where gravity loosens its grip, where the pull of the ground feels more like a whisper than a command. On such a planet, the air would thin, the sky would widen, and every step would feel like walking on the edge of flight. The familiar weight of your body would fade until motion itself seemed effortless, dreamlike. If Earth's gravity were only half as strong, mountains would stretch impossibly high, their peaks piercing the upper atmosphere. A single leap could carry you several meters into the air. You could throw a stone and watch it glide, curving slowly through the hazy horizon. Raindrops would fall like drifting beads, and rivers would carve wider paths as the pull of erosion weakened. Everything would move in slow motion, graceful, suspended. In this lighter world, evolution would favor height and delicacy. Plants would grow tall, their trunks hollow, but flexible, rising hundreds of meters toward a pale sky. Branches could stretch like wings, catching faint breezes that last for days. Animals might be elegant, almost weightless, thin-limbed creatures with wide lungs, gliding membranes, and hollow bones. Flight would not be a dream, it would be a birthright. Civilizations under weak gravity would think differently too. Their architecture would soar towers like filaments reaching for the clouds. Bridges could span entire valleys. Even motion would feel symbolic. To walk might mean to drift, to fall, to fly. The boundary between ground and air would blur, yet in the beauty of lightness lies fragility. A thinner atmosphere would mean less protection. Cosmic radiation, solar wind, and meteor dust would strike the surface more often. Fires would burn slower, but storms could tear across the sky for weeks. The planet would shimmer, fragile, breathtaking, but perilous. You can almost picture it, a blue world of floating forests where sound carries softly and footsteps barely mark the dust. Life there would evolve to dance with the air, not fight against it. Weak gravity gives freedom, but it also takes away the anchor that holds meaning. Perhaps then Earth's perfect balance between burden and lift is what makes our existence not only possible but poetic. The moon steadies our spin, gravity sculpts our form, yet all of this would mean nothing if our planet had been born in the wrong place. A few million kilometers nearer to the sun and oceans would boil into mist. A few million farther, and they would freeze into silence. Earth exists in a fragile corridor between inferno and ice, the Goldilocks zone, where the conditions for life are just right. You can picture it drifting outward from the sun's blinding furnace. Mercury blazes like a molten coin. Venus follows, wrapped in suffocating clouds of carbon dioxide, a planet where rain turns to acid before it ever reaches the ground. And then, far enough for sunlight to soften, there it is, a pale blue world. Here water flows freely, clouds cool the land, and life stirs in the shadows of ancient tides. Go a little farther still, and you meet Mars, smaller. Colder its rivers long turn to dust. The Goldilocks zone is not a static ring. It breathes with the pulse of a star. As a sun brightens, its warmth pushes that habitable zone outward, erasing worlds once safe within it. Planets are tested not only by birth but by time. To endure life must evolve faster than the star ages. On Earth, this fragile balance holds only because of countless coincidences: a gentle tilt of 23.5 degrees, an atmosphere dense enough to cradle warmth, but thin enough to let light through, a moon that slows our spin, keeping climate steady. Every factor leans against another, like stones in an arch. Remove one and everything falls. Astronomers have found hundreds of worlds orbiting distant stars, some resting neatly inside their own Goldilocks zones. But being just right is not enough. Balance is a moving target, and stability is rare. Perhaps the real miracle is not where Earth orbits, but that it has remained balanced long enough for life to learn how to see itself reflected in the stars. And so from this narrow refuge of temperature and light, life took its first trembling breath, a breath carried by water, nurtured by chemistry, and watched over by the quiet rhythm of the sun. Every star is a different kind of sun, and every world beneath it sees a different universe. Light is not merely brightness, it is a law, a sculptor, a language that teaches matter how to live. Its spectrum decides the colour of oceans, the rhythm of photosynthesis, the very hue of survival. Our world was painted by a yellow star, a calm G-type sun radiating warmth at just the right intensity. Under this glow, chlorophyll thrives, bending light into the greens of forests and the blues of seas. But shift the spectrum slightly, and the entire story of life changes. Imagine orbiting a red dwarf star smaller and older than the sun. Its light is dim, tinted with copper and blood. Days would pass in a deep perpetual dusk. To absorb such weak energy, plants could no longer be green, they might evolve black-purple, or dark crimson leaves trapping every photon that falls. The world would glow faintly like a bruise alive in shadow. Now travel toward the opposite extreme, a blue-white giant blazing with ultraviolet fury. Under its light air would shimmer, shadows would be sharp as glass. On such a planet, life would need armor, reflective shells, mirrored fronds, perhaps crystalline skin to scatter radiation. Forests might gleam gold or silver, a dazzling defense against their own sun. Light also determines rhythm. Around faint stars, days can last weeks, allowing life to slow its heartbeat. Around hot ones, time moves faster. Evolution races against decay. Even color becomes a measure of lifespan. The red star burns for trillions of years. The blue star dies young, brilliant but brief. Scientists studying exoplanets read these colors as codes. When the James Webb Space Telescope splits their light into spectra, each hue whispers a secret, the trace of methane, the shimmer of water, the faint fingerprint of biology. Color is more than beauty, it is biography. It tells us how stars feed life, how energy becomes memory. Perhaps somewhere another world waits beneath a foreign sun, its life forms turning not green but silver, not blue but violet, each one reflecting the color of the star that taught them how to live. If life exists beyond our world, it must find a way to eat the light of alien suns. Photosynthesis. The quiet miracle that turns photons into food may be the universe's most adaptable invention. On Earth it began in oceans when microscopic cells learned to trap sunlight through chlorophyll, releasing oxygen as a byproduct. That discovery changed everything. The air we breathe is the echo of ancient light. But under different skies the chemistry would change. On planets orbiting dim red stars, sunlight arrives weak and long, stretched into infrared. There organisms might evolve pigments that drink deeply from those wavelengths, molecules darker than black absorbing every flicker of energy. Instead of green forests, their landscapes might shimmer in violet or deep maroon. Around brighter stars the challenge reverses. Too much light, too many ultraviolet rays. To survive, plants might grow reflective leaves coated in metallic dust, shimmering like mirrors to protect fragile tissues beneath. Some may even bury their photosynthetic layers underground, harvesting filtered light through transparent veins. Scientists at NASA and ESA already model these possibilities using simulated spectra to imagine alien photosynthesis. They predict worlds where light drives chemistry far slower or faster than on Earth, where oxygen may not even be the main breath of life. So when telescopes gaze into the darkness and see the faint glimmer of a strange planet, they are not just measuring brightness. They are searching for rhythm, the pulse of light transformed into life beating quietly beneath another sun. From the gentle chemistry of light and oceans, the story of life turns back toward its most violent origin, a cosmic collision that forged the world we now stand on. Balance, it seems, is never born of stillness. The calm of Earth, the rhythm of its tides, the stability of its spin all trace back to an impact so immense it nearly erased the planet itself. 4.5 billion years ago, our solar system was chaos incarnate. Dust, ice and rock swirled through a disk of gas, forming young worlds that danced too close to one another. Among them was Theia, a planet roughly the size of Mars. For millions of years it drifted in a resonant orbit near the newborn Earth, two bodies circling destined to meet. When the collision came, it was not a gentle merging, but a titanic strike. Theia hit Earth at an angle, carving deep into its crust, vaporizing oceans, and turning the sky into liquid flame. The energy released was beyond comprehension, a force 1 billion times greater than all volcanic eruptions combined. For a brief epoch, Earth became a sphere of molten rock, its atmosphere stripped away, its surface glowing hotter than the sun. Around this blazing sphere, a halo of debris formed a ring of dust and molten glass stretching tens of thousands of kilometers. Slowly, gravity began to weave order from chaos. Over centuries, those fragments gathered, cooling into a single luminous companion. That was the birth of the moon, not captured, but created. Geologists read the evidence in silence. Earth and moon rocks share the same isotopic fingerprint, identical in oxygen and silicon ratios. They are siblings separated by collision, bonded by fire. And without that impact, the world would have been unrecognizable. No tides to stir the coasts, no lunar gravity to steady our spin, no long nights brightened by a silver reflection. Life, if it emerged at all, might never have endured. So when you look up and see the moon tonight, remember it is the scar of creation, the still glowing memory of the day the Earth was broken and remade. When the newborn moon locked into orbit, Earth's surface began to pulse with a rhythm older than language, the tides. Twice a day the oceans rose and fell, pulled gently by lunar gravity. What began as a celestial tug-of-war became the first heartbeat of our planet, a pulse that would one day guide the emergence of life itself. Picture an ancient shoreline billions of years ago. The air is heavy with mist, the sky dim with volcanic haze. The sea stretches into a horizon of silver, and with each rising tide, warm water spills into shallow pools. In those pools, organic molecules mix amino acids, lipids, tiny chains of carbon. The tide retreats, the water evaporates, and the compounds concentrate under the faint heat of the sun. When the sea returns, it stirs everything again like a slow cosmic experiment repeating endlessly. Within these cycles, chemistry became memory. Some molecules began to fold to react to copy themselves, and in that repetition the groundwork for biology was laid. The tides gave time and rhythm to the impossible they taught matter how to persist. Eons later, the same lunar pull shaped life's next ascent. Small marine creatures trapped in tidal flats learned endurance, how to survive in both water and air. From them came fins that grasped mud lungs that sipped oxygen bodies that crawled. The moon from its silent distance was the unseen mentor of this transformation. Even now, every living thing still carries that rhythm. Our hearts beat with saline blood that echoes the chemistry of ancient oceans. Our internal clocks mirror lunar cycles, tides turned inward. Fishermen, coral reefs, even trees still follow that same pattern of rise and rest of gravity turned to ritual. Without the moon's steady hand, our planet might have known only stillness. No tides to stir the shores, no gentle testing ground for adaptation. The boundary between sea and land would have remained unbroken, life imprisoned beneath the waves. So when you stand before the ocean and feel its pull at your feet, remember this motion is inheritance. It is the breath of the moon moving through time, the rhythm that lifted life from water to world. Long after the chaos of the Theia collision had cooled, the moon's work was not done. Its gravity did more than sculpt tides, it steadied time itself. Without that silent satellite, Earth would spin fast to tilt wildly, and seasons would swing between inferno and ice. The moon became the anchor of our climate, the quiet regulator that allowed life to evolve in peace. Imagine Earth without it. Over millions of years, the tilt of our axis, now a graceful 23 degrees, would lurch unpredictably from near upright to nearly sideways. Winters would bring darkness for decades. Summers would burn continents dry. Oceans would freeze thaw and flood in endless cycles. No species could adapt fast enough. The planet would be a pendulum of extremes swinging endlessly between chaos and calm. But the moon holds that chaos in check. Its gravitational pull tugs against Earth's wobble, smoothing it, slowing it, lending rhythm to climate and season. Because of this delicate balance, snow falls where it should, monsoons arrive on cue, and photosynthesis follows a reliable clock. The lunar presence has given the biosphere something more precious than warmth predictability. You can feel it in subtle ways. The length of a day, 24 hours, is the result of lunar breaking a gift of friction through gravity. The steady pacing of the seasons, the gentle transition from spring to summer, is an artifact of this cosmic partnership. Even our calendars, our sense of time itself, trace their lineage to the moon's restraint. Scientists studying Mars find the counterexample written in red dust. With only 2 tiny moons, its axis wobbles chaotically, swinging more than 60 degrees. Ice caps migrate. Storms engulf the planet for months. Their climate is a roulette wheel. On Earth, it is a heartbeat. So when you look up at the full moon, realize it is more than a companion. It is the architect of our calm. It holds the invisible balance that keeps rivers flowing, winds shifting, and forests alive. Life could rise only where time itself was gentle enough to learn. And that gentleness came from a collision that refused to fade. Before there were clouds, before rivers could carve the land, Earth was a world of flame. Its surface glowed with molten rock, its skies thick with vaporized metal. Oceans could not exist here. Any hint of moisture would have boiled away into the vacuum, and yet billions of years later our planet glimmers blue wrapped in seas that cradle life. How did a furnace become a water world? Scientists have traced the story written in hydrogen itself. The water in Earth's oceans carries a specific chemical fingerprint, the ratio of deuterium to hydrogen. That signature matches not the gases of the early solar nebula, but the frozen water locked inside carbonaceous asteroids and comets. These ancient wanderers born beyond Jupiter are now seen as the true couriers of our oceans. Imagine the scene: the young solar system chaotic and unfinished, planets still forming their orbits unstable. Jupiter and Saturn, colossal and restless, drift outward, tugging billions of icy fragments from the Kuiper belt and Oort cloud. The inner system becomes a storm of collisions, comets, asteroids and planetary debris raining down upon the newborn Earth. Each impact is violent beyond imagination, releasing heat greater than 1 million volcanic eruptions. Yet within every strike, ice melts into steam, mingling with rock vapor rising skyward. For millions of years, this bombardment continued, a cosmic downpour of stone and ice. When the world finally cooled, that vapor condensed. It rained for centuries without pause. Drop by drop, oceans gathered in craters left by the very impacts that delivered their water. The same violence that scarred the planet also softened it, transforming fire into sea. Even now, when meteorites streak through the atmosphere, some still carry trapped water, ancient frozen fragments of that era. They remind us that our oceans were a gift from beyond. Water did not belong to Earth. It arrived as an inheritance written in the language of gravity and time. Every wave, every raindrop is a survivor of that long voyage, a relic of the cosmos that crossed the void to make a barren rock capable of reflection, chemistry and life. Long before there were oceans, before Earth had even cooled, the universe was already experimenting with chemistry. In the vast molecular clouds drifting between stars, enormous nurseries of dust and frozen gas, the first organic compounds began to form. These clouds, stretching for trillions of kilometers, are not lifeless emptiness. They are laboratories of time. Here, under the faint pressure of starlight atoms, learn how to bond, and the alphabet of life begins to take shape. Hydrogen, carbon, nitrogen, and oxygen, the same 4 elements that compose every living cell, mingle in icy darkness. Ultraviolet radiation from nearby stars acts like a cosmic spark, breaking and reforming bonds, creating alcohols, aldehydes, and amino acids. Within these frozen veils, molecules layer themselves on tiny grains of dust grain by grain, reaction by reaction. And as new stars ignite within the same clouds, their heat and winds scatter this organic snow into the surrounding void. Astronomers have seen it. With telescopes like ALMA and the James Webb Space Telescope, they have detected the spectral fingerprints of methanol, formaldehyde, glycine, and even simple sugars inside nebulae such as Sagittarius B2 and Orion KL. The evidence is unambiguous: chemistry precedes biology. The universe, it seems, has been preparing for life long before any planet was ready to receive it. Fragments of that chemistry still arrive today. The Murchison meteorite, which fell in Australia in 1969, contains more than 70 distinct amino acids molecules older than Earth itself. Comets like 67P studied by the Rosetta probe reveal the same compounds frozen beneath their crusts. These are not random coincidences. They are echoes of stellar forges, proof that the seeds of life drift freely through space. You can imagine those molecules as ancient travellers, dust-borne messengers carried by light and gravity, waiting for a warm surface, a drop of water, a spark. When they finally met Earth, they found all 3. Perhaps that is the true origin of life, not invention, but inheritance. Every cell that breathes today carries the memory of a nebula, the chemistry of dying stars, and the patience of a cosmos that learned molecule by molecule how to dream. When the newborn Earth finally cooled enough to hold an atmosphere, the skies were a theatre of violence. Black clouds rolled over oceans of lava charged with methane, ammonia, and carbon dioxide. Lightning ripped the sky thousands of times each second, bright enough to illuminate entire continents. The air shimmered with energy, and in that turmoil, chemistry began to dream. Every bolt was an equation written in fire, an experiment that no mind had yet designed. Billions of volts tore through the thick air, splitting molecules apart and forcing them to recombine. Hydrogen met carbon, nitrogen joined oxygen, and new compounds flickered into existence. In laboratories eons later, Stanley Miller and Harold Urey recreated that primeval storm inside glass. When their electric sparks danced through a mixture of early Earth gases, something remarkable appeared: amino acids, the building blocks of life. From mere lightning, nature had written its first sentence, but there was another mystery hidden within those molecules: chirality, the property of handedness. Every amino acid comes in two mirrored forms, one left-handed, one right-handed. In theory, both should occur equally. Yet every living organism on Earth, from bacteria to trees to you, uses only the left-handed kind. The question remains, what broke that symmetry? Some scientists suggest that circularly polarized light from ancient stars favored one form, a cosmic fingerprint stamped across our chemistry. Others propose that cosmic rays, high-energy particles racing through the infant atmosphere, altered molecular bonds, introducing a subtle preference. Lightning, guided by magnetic fields, may have twisted the reactions themselves, giving birth to the first biological bias. Imagine that storm again, the sky alive with electric veins, the sea boiling beneath. Each flash created trillions of new molecules, each with a chance to lean slightly one way. Over countless storms, one direction won. From that simple imbalance came the spiral of DNA, the twist of proteins, the rhythm of metabolism. And so, from chaos came order, not imposed from above, but born within. That first flicker of molecular preference became the foundation for every living thing that would follow. The left-handed amino acids became language, architecture, and memory. Each cell that divides today still carries that original orientation, that primordial choice made under the red lightning of a world just awakening. You can almost hear the echo of those storms when thunder rolls today. Each flash is a faint reminder of that ancient moment when electricity met chemistry, and the border between inert and alive began to blur. Somewhere in that storm, matter crossed the invisible threshold into meaning. Perhaps that first imbalance was not chance at all, but the universe's earliest act of intention, a subtle tilt that set everything in motion. From the electric heart of the storm came polarity, pattern, and purpose. Every heartbeat that follows still carries that pulse, a distant memory of the first storm that taught matter how to live, and perhaps how to choose. Everything we are began in an explosion of silence, the Big Bang. From that moment, 13.8 billion years ago, energy condensed into matter, and the simplest elements, hydrogen and helium, filled the newborn cosmos. In the hearts of the first stars, those elements fused into heavier ones, carbon, oxygen, nitrogen, iron. When those stars died, they scattered their ashes across space-seeding galaxies with the ingredients of life. Billions of years later, one grain of that dust became our world. Volcanoes built the crust, lightning-shaped molecules, and comets delivered water. Chemistry turned restless. Molecules began to copy themselves, to change, to remember. The line between matter and life blurred until it disappeared. From the heart of a supernova to the twist of a double helix, the chain remained unbroken. Each atom in DNA once burned inside a star. Every strand of hair and leaf and cloud is made of recycled light. When you breathe, you exchange particles older than the Earth itself, hydrogen from the Big Bang, oxygen from dead suns. But the miracle lies not only in our composition, it lies in our awareness of it. The same particles that once drifted through space now assemble. Thoughts build memories, compose music. The universe has learned to observe its own reflection. Every neuron that fires is a small echo of that first ignition, the moment when energy decided to become experience. If you could follow a single atom through time, you would trace an odyssey more ancient than myth. It would pass through stars, oceans, and living beings, changing its companions but never its essence. The calcium in your bones might once have rested in coral beneath an ancient sea or floated in the atmosphere of a long-dead world. Existence is not a line but a loop, the same dust endlessly rearranging itself into consciousness. Perhaps that is the universe's quiet secret: it was never separate from us. The cosmos became conscious through its own dust, teaching itself to think, to question, to dream. What began as plasma and light now whispers through human breath. When we look to the stars, we're not seeking origins, we're remembering them. Life then is not an accident, but a continuation, the universe folding back to know its origin. From the fire of creation to the pattern of DNA, the same story repeats: energy, memory, and wonder. And as we stand here made of atoms that once belonged to stars, the cosmos finally understands what it has always been, aware, alive, and still unfolding. When astronomer Frank Drake first turned his radio telescope toward the sky in 1961, he was not searching for a single message. He was searching for a pattern, a mathematical way to measure the possibility that we are not alone. What he created became known as the Drake equation, not a formula of certainty, but a map of wonder written in numbers. Instead of symbols, imagine it as a chain of cosmic filters. First, the rate at which stars are born in our galaxy, millions every century. Then, the fraction of those stars that have planets. Around many of them, some worlds fall into the habitable zone, where temperatures allow liquid water to exist. On a few of those worlds, chemistry turns restless and life begins. On fewer still, intelligence awakens, and of those only some learn to send signals, the first whispers across the dark. Drake's idea was simple but profound. If you multiply those probabilities together, you reach a number, the potential count of civilizations capable of communication. Even when the inputs are cautious, the result almost never reaches zero. With hundreds of billions of stars in the Milky Way and billions of galaxies beyond it, the equation suggests that life is not a miracle of chance but a statistical expectation. Yet beyond the numbers lies a quiet truth. The Drake equation is not just about mathematics, it is about longing. It reflects a universe that might be designed for emergence, where matter seems compelled to organize, to awaken, to speak. Each planet that cools becomes another test of that same instinct, the instinct to become aware. Imagine a world orbiting a faint red star. Its seas shimmer under twin moons, its storms roll over continents of copper sand. Somewhere beneath those clouds, lightning strikes a tidal pool, and the same ancient chemistry stirs again. The constants of nature do not change, only the stage shifts. Perhaps life is inevitable because the universe is restless. The Drake equation does not count civilizations. It counts the persistence of curiosity itself, the cosmos, forever trying to know what it already is. Everything in existence, from drifting hydrogen atoms to the spiraling arms of galaxies, moves under a single law transformation. The universe is not a still canvas, but a restless engine unfolding in waves of complexity. From the first flicker of creation, it has been teaching itself to organize chaos into form, energy into memory, silence into meaning. At the beginning, evolution was purely physical. Gravity pulled invisible clouds of hydrogen together, compressing them until the first stars ignited. Inside those stellar hearts, fusion worked patiently, forging heavier elements, carbon, nitrogen, oxygen, iron. When those stars died, they scattered their creations into space, leaving clouds rich with material for the next generation. Each cycle left the universe more capable of building worlds, as if every explosion wrote a new instruction into matter itself. On cooling planets, chemistry became the next apprentice. Molecules collided, bonded, and broke apart again. Some patterns endured, others faded. In those endless exchanges, the seeds of selection appeared. Matter began to favor what lasted. Over time, simple chains learned to copy themselves, and the cosmos crossed an invisible line. Physics had turned into biology. Through that same process, awareness emerged. The ability to sense, to learn, to respond. Eyes evolved to gather starlight, minds to reflect on it. The universe began to perceive its own origins through living beings. Each neuron firing was a distant echo of fusion in a star, both driven by energy-seeking stability through change. Now that pattern continues through us. Our telescopes reach across time, watching galaxies evolve. Our technology adapts, learns, and reshapes reality in return. Evolution no longer stops at flesh and bone. It flows through language, through machines, through imagination itself. Every poem, every algorithm, every act of curiosity is the same force that once shaped suns, the drive of the universe to know itself. Even consciousness, fragile and fleeting, follows the same principle. Ideas rise and fade like stars. Memories collapse into new thoughts. Human civilization grows through invention and destruction, mirroring the cycles of galaxies. Our stories, like nebulae, are clouds of meaning forming into light. Each generation rewrites the universe in symbols, art and science, reflections of an endless pattern repeating through time. The cosmos is not finished. It is a story still being written, one that uses stars as ink and consciousness as punctuation. From gravity to thought, from particle to idea, it continues its grand experiment. And when you look up at the night sky, what you see is not distance but process. The the universe still becoming and somehow becoming you. It is the same law that drives atoms to bond and minds to dream a longing to evolve, to connect, to turn chaos into understanding. Every heartbeat, every discovery is a continuation of that cosmic sentence, stretching endlessly forward into the dark. Throughout the vast history of the cosmos, one principle repeats endlessly. Creation follows destruction, and destruction gives way to new beginnings. Stars ignite and burn only to collapse into darkness. Galaxies collide and merge. Species appear, flourish, and vanish. What seems like an ending is rarely final. The universe conserves energy and matter recycling, both turning apparent loss into fertile ground for the next chapter of existence. Consider a massive star at the end of its life. Its nuclear fuel, exhausted gravity, overcomes its outward pressure, crushing the core, while the outer layers explode in a supernova. For a brief moment, the dying star shines brighter than an entire galaxy. Its remnants scatter carbon, oxygen, iron, and other elements across space-enriching interstellar clouds. Those clouds will later condense into new stars, planets, and perhaps in the right conditions, life itself. From death comes the potential for creation. From collapse emerges opportunity. The same pattern resonates on our own planet. Mass extinctions, once viewed as catastrophic failures, are now understood as inflection points in evolution. The end of the dinosaurs cleared ecological niches, allowing mammals to diversify. The Ordovician extinction reset ocean ecosystems, paving the way for new forms of life to emerge. Each extinction, harsh though it was, enabled renewal and complexity to increase. Even within living beings, the cycle is mirrored. Cells die and regenerate. Tissues renew themselves. Molecules are broken down and repurposed. Every heartbeat, every breath is part of this rhythm of decay and reconstruction. Our own existence mirrors the universe, a continual process of turnover that fuels growth and adaptation. You can imagine the universe breathing in waves, expansion and contraction, birth and decay energy cycling through galaxies, planets, and living systems. Nothing is wasted. Leaves fall, storms, rage, stars explode, and life continues transformed by each passing event. This pulse moves through every scale, from the heartbeat of a sparrow to the rotation of a spiral galaxy. Even the pauses between breaths are part of the same song, a universal rhythm that never truly stops. In that way, time itself becomes a living process, looping endlessly through creation and collapse. The mountains that crumble into sand will one day rise again as stone. The oceans that evaporate will return as rain. Even civilizations follow this law. They rise, peak, fade, and leave behind knowledge that becomes soil for the next to grow. Nothing disappears, it only changes its form, waiting for its next expression. The cycle of renewal reminds us that endings are never final, and beginnings often require collapse. From the death of stars to the fall of species, from molecular turnover to human thought transformation, is the constant, and continuity is the reward. It is a rhythm written into matter, energy, and consciousness alike, guiding the universe and all within it toward persistence, adaptation, and an ever-deepening complexity that turns destruction itself into creation's most faithful servant. It began not with sound, but with stillness. A silence so dense that it carried within it every vibration that would one day become matter, light, and thought. Out of that silence came a pulse, the first rhythm, the first breath of existence. From that breath came hydrogen and helium, the simplest notes in a cosmic song that has never truly ended. From those notes, stars were born. They burned for millions of years, learning how to turn light into structure, how to weave time into form. In their cores, they forged the elements of everything that would one day see and feel and wonder. Carbon, oxygen, iron, the alphabet of being, all written in fire. When those stars died, they scattered their ashes into the dark, and from that ash new stars emerged, new planets spun, and somewhere on one of them a spark began to remember. That spark is you. The hydrogen in your body is older than the galaxies. The calcium in your bones once belonged to a dying sun. The oxygen you breathe now once flowed through the veins of 1,000 worlds. You're not merely standing beneath the sky, you're part of the fabric that allows it to exist. For billions of years the universe rehearsed this moment. It tried. Combinations failed, began again. It folded dust into planets, water into oceans, chemistry into memory. The same laws that guide the orbit of moons also shape the spiral of DNA. Life is not an interruption of the cosmos, but its continuation, matter learning to reflect on itself. Imagine the long journey of every atom in you. drifting through the void drawn by gravity, burned in stars ejected into nebulae, frozen in comets, falling through atmospheres dissolved in oceans lifted again into breath. Each atom has crossed millions of kilometers, has known heat and silence, chaos and form, and now they rest in you, organized for a brief moment into something that can look back. When you stare into the night, you're not looking into distance, you're looking into time. The light from each star began its journey before you were born, before Earth had language, before the oceans had names. Some of those photons have traveled billions of years to reach your eyes, and the moment they touch you, the circle closes. What was sent out has returned to its origin. Listen to the quiet between heartbeats. That pause carries the same rhythm that guides galaxies. The universe expands, you inhale. The universe contracts, you exhale. Every cell participates in that same cadence. The breath of the cosmos flows through you as surely as it flows through suns. There is no edge, no center, no true distance. The boundary between you and everything else is only a change in density. The same atoms that now form your skin will someday drift into the air, into trees, into other lives. What you call you is only a temporary constellation of matter on pattern in a long shimmering sequence. And yet within that impermanence lies something extraordinary awareness. The universe has achieved the impossible. It has become conscious of itself. Through your eyes it witnesses its own history. Through your questions it measures its own vastness. Through your curiosity it rediscovers its own laws. You're not a bystander. You're the voice of the cosmos made audible. If you listen carefully beneath the hum of thought, you can hear it breathing a low, endless exhale of creation. Stars are born, die, and rise again. Matter cools, warms, and forms again. Time folds, unravels, and begins again. And through it all, a single awareness flows, the recognition that existence itself is enough. When the last stars fade and the final photons drift into the dark, the story will not end. It will continue in memory, in the trace of what was once light, in the echo of what was once you. The cosmos will rest just as you do now, in the certainty that nothing truly vanishes, it only transforms. So close your eyes, breathe with it, let the distance dissolve. You're older than every star and younger than every dream. You're the silence before creation and the thought that follows. You're not part of the universe, you're its awareness, its reflection, its return. And in this stillness, as the stars turn and time exhales, one truth remains unchanged. You have always been the universe, and the universe has always been you.